Okay, so ready to start section 9.4, addition and subtraction of radicals. So the very first thing we want to do in concept 1 is look at what the definition of a like radical is. So I just want to come off to the side a moment and just remind you a little bit about like terms. Right. So when we add or subtract like terms, like polynomials, right? Remember the big thing is that like terms have the same variable factors, right? In other words, we have the same letters with the same exponents, right? So if I, just an example, right? If I had like 2x squared plus 5x squared, right? I can combine these two things because these are like terms, right? So 2x squared plus 5x squared is 7x squared, right? And you can actually easily see this, right? If we factor out the x squared out of each term, so we get 2 plus 5 left over, so this becomes x squared times 7, which is the same thing as 7x squared, right? So we're able to, know that we can add like terms together because of factoring out the common variable factors, right? So an example where we don't have like terms, right, would be like, if I have like 2x squared plus 5x squared, let's say y squared, I'm going to put a y there, right? So we have 2x squared y plus 5x squared y squared. And those are not like terms, right? The difference is here with the, oops, I don't want to make that a 0. Let me just draw an arrow. Between these two exponents on the y, right? They both contain the same letters, but not all the letters have the same exponents, right? Because this is understood that's a 1, right? So to easily show this with factoring, what we could factor out of everything would be x squared y, right? So then what you would have left in the first term would just be 2 plus and then 5y, right? Because we need that extra y to make that be y squared. So notice that these two things I can't add together, right? So in other words, these are not like terms. So that means I can't add them together, right? So that's just a quick refresher on like and unlike terms for polynomials. So let's now define. So definition of like radicals. Right? So two radical terms are called like radicals if they have the same index and the same radicand. Right? So just as a quick refresher, like if I have the third root of, x squared, right? Then this whole part, x squared, that's called the radicand, right? It's the part underneath the radical. And remember, this part is the index, right? And also just a quick refresher that if I just had like the square root of 5, right? The index here is 2, right? It's understood that that's a 2 if there's no index written, right? That's a square root. And of course here the radicand would be 5, right? All right. So just a quick example of this, right? Just to help you see this. If I have 3 square root of x plus 7 square root of x, then just like before, I could factor out the square root of x, so then we're left with 3 plus 7, right? And this becomes square root of x times 10, and then I could apply the commutative property of multiplication, right, which says that it doesn't matter the order I multiply things in, right? 2 times 3 is 3 times 2, so this just becomes 10 square root of x. Just a little easier way to write that. Right, normally when you have something times a radical, you write that something first, right? That other factor. So that way it's not confused. Like if I write square root of 10x or x10, it's not real clear. Is the 10 underneath the radical sign? Like what's going on with that? So that's why we typically write it like this, right? So if I would have had like 3 square root of x plus 7 cubed root of x, I could not add these together, right? These are not like terms, right? They're not like terms because they don't have the same index, right? Also, if I had something like 3 square root of x plus 7 square root of 2x, I cannot add these together either, right? These are also not like terms because the part underneath the radicand is not the same, right? So there's two conditions, right? The first is that they have to have the same index, and the second is they have to have the same radicand, right? Both of those have to hold true. Right? So in example 1 here, I have add or subtract is indicated, right? So the first one, we're subtracting. So we have 5 radical 6 minus 8 radical 6. So here I could just factor out a radical 6, right? So we get 5 minus 8, which equals radical 6 times negative 3, which is the same thing as negative 3 radical 6, right? The next one here, we have radical 10 plus radical 10, right? It's important to note this is 1 times radical 10 plus 1 times radical 10, right? It's just like if I had, x plus x, that's the same thing as 1x plus 1x, which is 2x, right? Same idea. So this would just become 2 radical 10, right? I have 1 plus another 1, so I have 2 of them total, 2 radical 10, right? If you wanted, you could factor out the radical 10 from both sides, and you would get 1 plus 1, which of course equals radical 10 times 2, and then that's just the same thing as 2 times radical 10. Right, so either way, so you can write it out by factoring it out, or just using kind of the same ideas as when we add variables together. Right, we don't normally write it that fashion. Maybe when you first learned it, but later on, it's not really necessary. Right, so in example 2, we have some more examples of this. So notice the very first thing I'm looking at is the radicand, right? Or excuse me, not the radicand, but the index. The index on all 3 of these is the same, 3. And then now we could look at the radicand. And notice all of them are xy, right? So since all those things match, these are like terms, right? So this is just going to be equal to 5 minus 3 plus 7 times the cubed root of xy, right? In other words, you're factoring out that common factor, the cubed root of xy. So this is equal to, so 5 minus 3 is negative 2, or excuse me, 5 minus 3 is 2, plus 7 is 9, so we get 9 cubed root of xy. Right. So then the next one here, maybe a little tricky because it's fractions, right? But notice again, if I pay attention to the index, right, that matches, right? It's both 2, and then the radicand is also the same, right? So if we go to factor that out, we would have 5/6 y plus 1/4 y. Oops, let me make that a little better. Times radical 2, right? So then I want to be able to add these two things together, right? And these two things are like terms, right? They have the same variable with the same exponent, so I can combine those two things. So, but we need to get like denominators, right? So a common denominator between 5/6 and 1/4 would be 12, right? So 5/6 times 2 over 2 times y plus 1/4 times 3 over 3 times y, all times radical 2, which this would equal 10/12 y plus 3/12 y times radical 2. So then 10/12 plus 3/12 will give me 13/12. Right, so we get 13/12 y times radical 2. Right. All right. So then the next couple of problems take a little more time because notice, you know, these examples we didn't have to reduce or simplify. We already had like radicals, right? So with the next couple of problems, we're going to have to combine some things that we learned from the last section with this section to be able to actually end up adding, subtracting these, right? We need to get them to be like radicals first, right? Like if you look at part A, the first radicand is 75, and then we're adding it with something with a radicand of 3, so those don't match. So we can't add those the way that they are, right? So the very first thing that I'm thinking about is what's the prime factorization of 75? Right? So 75 is equal to 5 times 15, right? So 5's prime, and 15 is 3 times 5. So in other words, 75 is equal to 3 times 5 squared, right? That's the prime factorization. So when I rewrite this, I could rewrite 75 as 3 times 5 squared, and then plus 2 radical 3, right? So then now what I can do is apply the multiplication property of radicals that we learned last section and split this apart, right? So this would be the same thing as radical 3 times square root of 5 squared plus 2 radical 3, which this equals, so the radical of 5 squared is just 5, right? So this would be 5 times radical 3, right, that first part, plus 2 radical 3. So now I can add these together, right? This would just become 7 radical 3, right? Because I have 5 radical 3s plus 2 radical 3s, and we get 7 radical 3, right? And if you wanted, I mean, you could factor out the radical 3, right? So that gives me radical 3 times 7, which is the same thing as 7 radical 3, right? All right, so the next one, this one we don't have to worry about prime factorization so much because we have just variables underneath the in the radicand, underneath the radical. So this would be 4 square root of a squared times square root of b, right? I can apply that multiplication property to split that up, right? This would be minus 6a times radical b. So the square root of a squared is just a, right? So this would be equal to 4a times radical b minus 6a radical b, right? So this would become 4a minus 6b times radical b, right? Just factoring out that radical b. So 4a minus 6b is equal to, oops, that should be an a. Sorry about that. 4a minus 6a all times radical b, right? So this would be negative 2a radical b. Right. So then the next one we have to worry about maybe some prime factorization. So this 2 is already prime, but the 18 and the 50 is not, right? So maybe come off to the side and just write that. So 18 is equal to 2 times 9, which 9 is 3 times 3, right? So 18 equals 2 times 3 squared, right? Then the other number we were kind of worried about is 50. So 50 is 2 times 25, which 25 is 5 times 5, right? So 50 is equal to 2 times 5 squared, right? So that can help me rewrite this. And then some other things to note is, remember, we don't want the exponent to be bigger than the index, right? The index is 2. So when I have this y cubed, I want to rewrite it as y squared times y, right? Because y squared is the biggest multiple of 2. That's less than 3, right? So when I come back over here, I would have negative 3 times the square root of 2 times the square root of y cubed. Well, actually, let me do something else first. Let's do minus 3 times the square root of 2y squared times y. So I'm just rewriting 2y cubed as 2 times y squared times y, right? Then I would have plus 5y times the square root of, and then 18, let's write that in prime factorization form. That was 2 times 3 squared, right, times y. Then we'd have minus 2 times the square root of, and then 50 was 2 times 5 squared times y squared times y, right? Because that's how we want to rewrite y cubed. So then this just maybe puts in a little easier form. So then we can use the multiplication property of radicals to rewrite this as radical 2 times the square root of y squared times radical y plus 5y times radical 2 times radical 3 squared times radical y minus 2 times radical 2 times radical 5 squared times radical y squared times radical y. Right, so we can split those apart for each factor. So then this first part, y squared just becomes y, so I would have negative 3 times y. And then these two, I can apply the multiplication property of radicals and just rewrite that as the square root of 2y, right, because they have the same indexes, and we're multiplying them. So this would be plus, so similarly here I want to clean this up. So I have 5y times, this would simplify to be 3, right? So 5y times 3 would give me 15y, and then we would have the square root of 2 times y, using the multiplication property of radicals for these two things, right? And then I would have minus, and then and then I would have 2 times, and then this guy, the square root of 5 squared would be times 5, right? And then the square root of this guy would be just times y, right? So in other words, this part becomes 10y, right? And then I would have the square root of multiplying these two things together, we get the square root of 2y, right, using that multiplication property of radicals. So then what we have then is negative 3y times radical 2y plus 15 times radical 2y minus 10y. This is 15y. Sorry. Negative 3y plus 15y, and then minus, we got 10y times radical 2y, right? And then I can pull out that radical 2y. So then what I have left is minus 3y plus 15y minus 10y. So if I combine like terms, right, we get 15 minus 3 is 12y, and then minus 10, so we get 2y times radical 2y, right, as the final answer. Right. So then the next one, we have 4 times radical 45 minus 5y to the fourth, and that's the square root of all of that, right? So 4 times radical 45 minus the square root of 5y to the fourth. So again, I want to try to simplify this as much as possible, right? So kind of what I'm focusing in on is what's underneath the radicand, or what's underneath the radical, or in other words, the radicand. So 45 is not prime, so that's equal to 9 times 5, which 5 is prime, and 9 can be broken down into 3 times 3, right? So when I rewrite this, I would have 4 times the square root of 3 squared times 5, right, as a prime factorization, and then minus the square root of 5, and then y to the fourth I can rewrite as y squared squared, right? So that would be 5 times y squared squared. So then this would become 4 times the square root of 3 squared times the square root of 5 minus the square root of 5 times the square root of y squared squared. Right, so just using that multiplication property of radicals. And then, this one and this one, these are the square roots of perfect squares, so I can simplify that. So that would be 4 times 3 times radical 5 minus, and then the square root of y squared squared would just be y squared. So this would be minus y squared times radical 5. So this is 12 radical 5 minus y radical 5, right? And then if I pull out the radical 5, I get 12 minus y squared. Right? So then, and just correct that. I forgot to write down the square exponent. Sorry about that. So when you pull out that radical 5, we get 12 minus y squared. That's the coefficient, right? And there's nothing we can do to simplify that, so you would just leave it like that, right? All right, so that's all I have for this section. Let me know if you have any questions.